that we're gonna be done with the Aubrey set and the Pierce barrier today, and then I'm gonna switch to giving you in the remaining set of lectures sort of like the very brief PD viewpoint of everything we have done. So um, uh, I mean that's the plan. I don't know how far I can go, but basically I will try to give you a crash course on like on a way to look into Hamilton-Jacobi equations from PD viewpoint, and then I'll start from the beginning from the method of characteristics, and then proceed. It's a bit non-traditional. It's a mixture of methods of characteristics and viscosity solutions. It has a little bit different flavor, but it's gonna be interesting. We're gonna do that from lectures 34 35 to 40 or something like that. Yeah, so to connect the dots, and that's gonna be the end of it, of the class. Once we are done with bridging between the PD viewpoints and the dynamical system viewpoint. Of course, I mean I can go on for like 20 more lectures to tell you deeply about the PD viewpoints, but that would could be probably too much. So so that's the plan. Yeah, so I would say that today is going to be the last lecture on Pierce barriers and Aubrey set. So today we're gonna finish up on Aubrey set and Pierre. I kept writing this one wrong. Barrier. Okay, and it's just rather interesting. I mean, the lecture is quite reasonably lengthy, and I there's one part that I didn't write down clearly, and I'll explain to you today. Um, and the main claim for today is that we have been always thinking of hxy as basically the cost of going uh, from x to y uh, in an sort of infinite amount of time, right? I mean, that's sort of roughly speaking, that's that. And surely you have the definition that h of xy, let me recall it, it's exactly that. So lim inf t goes to infinity of the cost of going from x to y in time t, right? I mean, the normalized one with c not taking into account, being taken into account. So you can imagine that you can view x, if you think of this one is a function of y maps to h of xy, you can imagine that x is kind of a fixed vertex. Okay. Essentially, you can think of it's like that. So you're given a fixed vertex, and you're trying to, for any y, you're trying to find what's going to be the sort of optimal parts going from here to here, and what's going to be the cost. And same for z. Here, it's going to be what's going to be the optimal curves going from y to z, x to z, and stuff like that. And so you fix a vertex, and you try to um, think of a function like that. But I mean, this is for those of you who are familiar with maximal solution. This is different from maximal solution. But anyway, if I think about it, this function like this, then the claim for today is gonna be the quite important claim. We're gonna prove that before. I mean, but I'll give you some review surely. The important claim we're gonna make today is that the function y maps to h of xy. You can define to be a vertex x. If let me check with my notion, I write, yeah, okay. Superscript h of xy, This is a Wickham solution. Okay. So that is a very important claim today that we're going to prove. By being a Wickham solution, we mean that this function h of x uh, is in S minus, right? I think minus is here. And this is equivalent to the fact that we have is dominated from above by L plus C naught. And for HY, there exists a backward characteristic, a calibrated curve. Gamma mapping from minus infinity 0 to the torus with gamma 0 equals to y. Okay, so that's sort of the equivalent definitions. Later on, again, you're going to see that this is actually nothing but equivalent to the fact that h of x is solving the PDE, h of y d h of xy equal to c naught in the torus in the viscosity sense. Okay, so that's sort of an important claim or theorem we're going to prove today. I wouldn't say that this is a big deal. I mean, we have been having two different ways to prove the existence of Wickham solution. This is sort of, in a way, a convenient consequence of what we have learned about peer barriers, that essentially, by developing this sort of mechanism, eventually we also come to another way to prove that there exists a Wickham solution, which is exactly this function, right? I mean, but again, I mean, we already have proofs for that in different ways. So I mean, this is in a way just a convenient consequence of, of, of the important properties of the peer barriers. Okay. So let me review very quickly. Last time we have defined the Albrecht set to be all points in which that you have going from x to x costing you zero cost, and uh, we have known that the Albrecht set contains the matter set, the projected matter set. So last time we already proved that the matter set, the projected matter set, is a uniqueness set. So from here, actually, you can also imply that the Albrecht set is also a uniqueness set. But I mean, I don't have time to go to this, but it's also a uniqueness set. By that, I meant that if you have two Wickham solutions, if they agree on the Albrecht set, then they're going to agree everywhere. Of course, I mean, this is a consequence of the fact that the projected matter set is already a uniqueness set, right? But there are other different proofs anyway. The proposition is quite clear. I don't need to remind you that, but basically, if it's in the Albrecht set, then essentially you can find loops with large time, so that going in each of the loops costing you essentially zero, right? I mean, going in from x to x in each of the loop costs you, roughly speaking, zero amount of cost. Okay. And what is also important is the characterization theorem that we proved that is equivalent to the fact that if you fix any delta greater than zero, then you take infimum along all the loops, but you only need to require t greater than delta. You don't need to take t goes to infinity. Still, if this is the case, then you would be able to conclude that it's an equivalent definition of the Albrecht set. Okay. Any question for me up to this point? I mean, on the review and on the sort of big pictures of everything. Okay, good. Right. So so let's do this one. I mean, the proof is not too hard, but it's actually quite beautiful in how to put it, I mean, like the intuition behind that is quite beautiful in a way. I am thinking of, okay, so I mean, how do I put it? So I would say that intuitively, okay, so this theorem is basically that I'm going to say that, so intuitively, like um we have the function h of x, y, right, which takes x as a vertex, and I mean, my way of thinking about this is that as we let the time travel, the time travel tend tending to infinity, you know um we let the time travel tend to infinite, I mean, we would have that, I mean, it's sort of like, it's like we let the vertex x, go into infinity. Okay, this is a very, very vague statement, but what I'm thinking about the function in a way is that, and you can see that actually evidently in the proof, is that I have, okay, so I mean, this is x, and surely it's connecting to y, right? and and of course, because the environment is periodic, right? So what I'm saying about infinity here is I'm thinking of Rn, with everything being periodic. So when I'm saying that I'm sending x going to infinity, you can see that, I'm using the fact that x is the same as x plus zn, right? I mean, it's in the same equivalent classes, whatever. So what I'm thinking in my mind is that I'm sort of kicking x going further and further away, like having the vertex sort of travel to infinity, and I'm observing what's just happening with y being kept. It's that's a vague way that I'm thinking about that, and I'll actually, it's quite helpful if we think about it that way. Anyway, it's quite vague. All right, so um, so let's do it, and you see what I meant. All right. Um, so yeah, so we have to prove two. So we have to prove 2 points, right? 2 points that we need to address. The first point is that I need to prove that the function h of x is dominated from above by L plus C naught. Okay. And the second point, that I would need to prove that the existence of um, calibrated curves. Right? I mean, that's exactly, I mean, going in the dynamical system way, that's exactly 2 points you need to prove. Okay. So the first point we're going to show is that we try to show that h of x is dominated from above by L plus C naught. And, that is equivalent to the fact that if you take, yeah, what's the best way to describe it? Um, yeah, I mean, never mind. Let me just start with the standard point, right? So the basic point is that if you take any curve gamma 0 to t, you know, piecewise C1, or piecewise C1, or absolutely continuous, doesn't matter, then the basic point we have been using throughout the whole course is that we have this, no, going from gamma 0 to gamma t is always dominated by the action function. All right, here again, I haven't normalized it yet because you know, if I add the normalization, I would need to add it to both of the side. I will do that later. So I mean, in terms of the picture here, right, if I'm going along the curve from gamma to 0 to gamma t, I always have to um, you know have to pay certain price that is dominated from above by the action functional L. Okay, that's not a problem at all. Now, what I'm doing is that I'm going to try to connect x to gamma 0. I mean, I'm trying to connect the dots, right? And you're going to see what I meant by that. So connecting the dot, I'm connecting from x to gamma 0 first, right? And when we try to connect the dots, then clearly, going in a, maybe let me write out, this takes an amount of time t prime, this takes an amount of time t, then it is clear as always that going from x to gamma 0 in t prime amount of time, then going from 0 to t, right? That going from gamma 0 to gamma t is always going to be greater than or equals to going directly from x to gamma t, right? It's always that sort of same trick about triangle inequality that we are using. Okay. And then again, as I said, I will need to add the normalized constant C naught. So I added it to both of the sides. So adding the normalized constant to the left-hand side and break it to two pieces on the right-hand side, I would have this. It's very standard, right? And then here is exactly the point that I'm sort of letting now. After this, right, we're gonna now let t prime goes to infinity, right? And again, geometrically, you can also think of kicking x to infinity, right? Again, I'm thinking of x, an equivalent class, maybe put equivalent class is better, is sort of x plus zn, right? So I'm thinking of sort of like kicking the point x going to infinity because it's in the periodic domain, letting, when I'm kicking x going to infinity, the sort of the travel time is getting larger and larger and larger. And then, I'm essentially having the same effect of, t prime going to infinity, right? So that's sort of a geometric way to think about that. So in this picture, you can see that I'm trying to let it goes to infinity. Okay, infinity. Right. So when it happens like that, I'm just gonna look at the left-hand side, right, of this point. The left-hand side, when I let t prime goes to infinity, I would have lim inf t prime goes to infinity of ht plus t prime x gamma t plus c naught t plus t prime, right? But again, lim inf of t prime going to infinity is the same as lim inf of t plus t prime going to infinity, right? So that meant that the left-hand side gave me nothing but just the peer barriers of going from x to gamma t, right? Which is hx of gamma t. Okay? So that's the left-hand side, very naturally. Yeah. Okay. So that's exactly that terms that I'm highlighting here on the left panel. Okay. Now the right-hand side, uh, I mean, you can use the equality or you can just use directly the inequality, right? Whatever the t prime I'm taking to infinity is always bounded by it's always bounded from above by the peer barrier going from x to gamma 0, right? X of gamma 0, and then this is just a normalized action, right? So therefore, eventually, we have been able to deduce that the hx of gamma t minus hx of gamma 0 is always bounded by the normalized action of gamma, right? So we are done. Okay. So You see, I mean, it's actually not something too complicated to visualize in terms of the picture, right? I'm given 2 points, gamma 0 and gamma t. I'm just going to recall the whole proof here. I would need to show that here I would need to show that hx of gamma t minus hx of gamma 0 is less than equals to the normalized action, right? So L plus C naught. Yes, that's what I had to prove, right? And then again, I have a vertex x there, and I was telling you that I was thinking of the fact that I'm sort of thinking of x here, and I'm sort of letting x traveling to infinity, right? So it's just going to be a part of infinite time amount, infinite length, essentially. And then, once it's traveled to infinity, um, it's like I'm kicking the vertex to infinity, and what I needed to do was just that I'm taking this sort of like very lengthy part, and I'm just connecting it with the given part to have a new one, and just by triangle inequality I can prove the result. Okay. So that's a way to think about it. Any question or concern up to this point? Okay. All right. So and then let's do the second part. So I'm actually skipping some details here, and I'm gonna discuss quickly with you. It's quite fun. Whatever. Um, yeah. So to finish the proof, now we need to start with. So the second point is to prove the existence of calibrated curves, right? With for, let's say, y given, right? Again, I mean, any given point y, you start with y, right? And then we need to find a calibrated curve so that along the calibrated curve you always have that or backward characteristics. You always have that the difference of the peer barriers is the normalized action. Okay, right. How do we do this? Well, I mean, let's take advantage of the definition, right? I mean, what's the definition of, of h of xy anyway, right? Um, because this is y given to me, right? Okay. So what's the value at this point? H of x as gamma 0 is exactly h of x of y, which is h of xy, right? So that's a ending point that's given to us. And then now let's exploit this piece of information to see, right? Because again, the point is that we need to generate um, we need to generate a full backward characteristics or full geodesic rays, right? And from h of xy, what we have is that h of xy is going to be equals to lim. There is a sequence of extremal curves, right? I mean, let me just write that. Limit at case goes to infinity by given sequence of extremal curves that we can find based on the previous proposition. L of gamma k dot, yes, plus C naught of tk, right? So yes, there exists a sequence of extremal curves. I should have said that with tk goes to infinity, such that tk goes to infinity, and um, so you would have that tk goes to infinity, and then your peer barrier equals to this. So, from here, we see naturally how it goes, right? Because we have the amount of time going more and more and more to infinity, right? And what it would suggest naturally is that I'm trying to use certain diagonal argument and stuff like that, sort of using conversion to exploit or to achieve a a part that have infinite amount of length, right? So it's clear that we're gonna use gamma k to to imply the existence of gamma, right? So that's a very natural way, and that's why it's really beautiful. Um, Yeah, I mean, I could have read, would have write things down that way, but I mean, to respect the fact that we are creating parts going from minus infinity to zero, then we need to do change a variable a little bit. So, I mean, gamma k here is going from 0 to tk. So you would change it to eta k. It's going from minus tk to 0. I mean, just do change a variable, right? And you would define eta k of s to be nothing but what but uh, gamma k, or let's see, uh, um, s minus tk, I believe, for zero hold on, uh, did I write correctly? S plus tk, I'm sorry, for minus tk less than equals to s less than equal to 0. Okay, just a little bit change of variable. Then we have eta k, right? So we would have eta k of minus tk equals to x, eta k of 0 equals to y. And remember that eta k is always bounded, right? It's only in the torus. Again, and then eta k in L infinity plus eta k dot in L infinity is always bounded. Okay. Yeah. So therefore, you can use the diagonal argument. Okay, so roughly speaking, the curve is like this, right? Going from that, it takes more and more time to go there. Again, I mean, you can extend it in a periodical way. The same. Uh, so it's bounded. So by a diagonal argument, you can find. Again, I'm using the same notation. So with the loss of generality, you can assume that eta k converge to gamma locally uniformly on minus infinity 0, um, again by passing to a subsequence if needed. Okay? So that's why, again, earlier we needed to develop a big regularity theory to understand about minimizers, right? Because we are using the fact that minimizers are nice, having bounded velocity and stuff like that all the times. Okay, so that was good. And and then this is exactly our candidate for our calibrated curve. Okay, right. Right. So now let's the final claim is that the final point, the final claim is that we're gonna show that indeed gamma is our needed calibrated curve, right? Clearly that the endpoint is going to be 0. Right? So how does it go actually? Um, let me try to draw a picture of that. I mean, it's not easy to draw actually, but let me try my best. So this is our gamma, right? It was the convergence of a sequence of eta, right? So I would have, maybe this is sort of eta 1, and then maybe this is eta 2, and maybe this is longer eta 3. Each of the eta is having a finite just finite amount of time, right? I would have eta k is just going from minus tk to 0 to the torus, right? And then but gamma is really from minus infinity to 0 to the torus. So those are the information we have, but essentially we have sort of like a family of curves that sort of converge locally uniformly to a curve that's sort of having infinite time, right? And that's exactly going to be the point that we are using to get the result. What we only need to show is that, so what do we need to show? We're going to fix t greater than 0. We want to show that uh, hx of gamma 0, which is y, okay, gamma 0 minus hx of gamma minus t equals to, right, for any time, equals to the action, normalized action, gamma dot es plus c naught times t. Okay, so that's what we wanted to show. Okay. Right. So let's see, how do we do it? Well, I mean, um, you can do it because of the fact that you can just select, you know, as uh, I have given you sort of a schematic picture here. You can just take all tk greater than t, right? And then you're gonna start with the action functional from the bigger term, right? You would start with the action functional for, you know, for the eta k, this integral eta k dot ds plus c naught tk. Okay, you start with a bigger term, therefore you can split it into two parts. The first part is something like smaller than t, right? Minus t. So you would go from minus tk to t, minus t of this amount. And then the other amount is from minus t to 0, the other amount. Okay. And then we see how it goes from here. So here's the step that I skipped. So let's just do the proof and then we discuss quickly about this. So, you know, so you see that there are two terms, right? This term, which is interesting because you know, t is fixed, but because I have tk is going to minus infinity, so therefore the first term, when I take the lim inf of k goes to infinity, right, or lim whatever, it's gonna be greater than or equals to the h, right? That's just a definition, right? Because, you know, going from uh, um, um, infinite amount of time to t, right? I'm using exactly the same idea here, right? Because you see the same idea was that I'm keeping this interval and then I'm gonna let the other interval, I mean, I'm gonna let this one travel to minus infinity, right? So that's the first term, that is always greater than equals to h of x of gamma minus t, right? The second term that I was keeping here was that I was claiming that I have this conversion, that the action functional of in a fixed amount of time of eta k of eta k converge to the action functional of gamma, right? So of course you can question me right away, right? I mean, am I cheating, right? Because I only said that I have eta k converge to gamma uniformly only, right? So why do I have equality? In fact, there are two ways to do this thing. The first simple way is that actually I don't even need equality if I want to do it in a vague way, but let's talk about that. So we're gonna discuss this one. Anyway, assuming that I have that conversion, then clearly that you see that the left hand side, I mean this box here, when I take lim inf of tk going to infinity, I would have that it's exactly by definition or by the proposition. This is exactly h of xy, right? So h of xy is going to be greater than or equals to h of x gamma t, gamma minus t, plus this cost function naturally, right? So therefore, what is really amazing is that, from that we have been able to deduce that h of x of y minus h of x of my gamma uh, gamma minus t is greater than equals to the action, right? And the other inequality, we already got it, right? We already got, because that's exactly from the fact that h of x is dominated by L plus C naught, right? So therefore we get the equality. So therefore we get the equality, and that's what we need, right? So you see that throughout the proof, the idea that is quite simple but relevant is that, you are going along the whole part, and then the idea was that you are kicking sort of the vertex traveling to far away to to infinity. Is quite helpful in the geometric picture. So essentially, at the end of the day, you lost track of it, right? Because you're sort of like letting it travel into infinity. Okay. Any questions for me or concerns for me up to this point? Okay, good. So let's discuss this point, right? So a quick discussion. I mean, some of you tell me, I mean, what's your thought on this discussion? So we had like eta k converge to gamma uniformly on st is fixed, right? Then the claim was that, y, that I have limit as k goes to infinity or am I cheating something here? Like any thoughts, any things you would like to point out? Okay. Um, so basically, we have actually something deeper here, right? I mean, what is really remarkable is that, how to put it, is that not just that we had, we not just that had that just eta k is having bounded velocity, right? We actually have that eta k's are minimizers, right? I mean, did I write it down? Let's see. Give me 1 second. Uh, yeah, eta k was created by gamma k's, and those extremal curves, those are minimizers, right? So we had deeper informations, and that's something that we should keep in our mind. Um, and then I claim that this is actually true. I mean, this conversion sounds magical, right? But it's not too magical. I mean, it's already here, right? I mean, of course, I mean, I am a little bit cheating here, but you're gonna see. So in fact, uh, so in fact, maybe this is point number one. In fact, that eta k is a minimizer, right? We surely have that eta k in our infinity plus eta k dot in our infinity um, is bounded. Okay, that's not a big deal. But also that eta k satisfy the Euler-Lagrange equation. Right? We haven't used it actually. Um, and let's write out the Euler-Lagrange equation, and you can see, I mean, like what what's the advantage of that? If you write out the Euler-Lagrange equation, what's that? D over ds. Correct me if I'm writing something wrong. Dv L uh, eta k of s eta k dot of s equals to dx L eta k of s eta k dot of s for minus t less than equals to s less than equal to 0, right? And then you can write this one down more explicitly. Right, so this is equivalent to, like if you do the differentiation, right? I mean, many times I skip the differentiation, but I'm doing it today. So let's see, if I do the differentiations, I differentiate in the first slot, I should have dx v L at the k dot. So this is a matrix of size n by n, right? And then I'm multiplying with a column vector. So I'm thinking of eta k dot as a column vector. Okay. And then I differentiate in the second slot, I should have d square of VVL eta k dot eta k double dot, right? Equals to dxl eta k dot. Okay, right? So so from here I can write down what's eta k double dot, right? And actually you can do it iteratively to write out any derivative of eta k. But I mean, what I only needed here is that this is gonna be giving me that eta k double dot of s gonna be equals to d square vl eta k dot. This is a matrix that is invertible. Remember that is positive definite, um, bounded between two constant, invertible. Uh, uh, I'm thinking of every vector today is a column vector, dxl at the k dot minus d square of xvl at the k. Okay, and you see now that as d square vl inverse, is bounded between two constant, whatever you want, c 1 over c, and then dxl d square xv l is bounded, right? Let me be careful because the eta k and eta k dot are bounded, so every term here is bounded. Right, so we actually have more, right? I mean, we would be able to deduce that not just that eta k is bounded, but eta k double dot is also bounded. Okay, and actually you can iterate this one, and in fact you can show if L is smooth enough, right? If L is in C infinity, then you would have that actually eta k in C infinity norm is also bounded. Oh, maybe let me be careful. CM norm is bounded. for any m. Okay, so that's really beautiful because of the fact that we have more, right? We have that the minimizers are surely smooth, or ck, I mean, or as smooth as the Lagrangian, but we also have that all the derivatives and everything about it. So clearly that, from here you can actually use Azela Ascoli, right? So use Azela Ascoli, whatever. No. To see that actually not just that eta k converging to gamma, but eta k converge to gamma in C1 norm, right? On minus T0. So I'm cheating here. I should have said that it's up to a subsequence. Okay. So when eta k converge to gamma in C1 norm, then clearly you would have L of eta k dot converge to L of gamma dot. I mean, this is in a classical sense, right? And hence the conversion earlier. Okay. Yeah. So you see that it's hidden here that's why this one is true, right? I'm using really deeply the fact that I have a nice minimizers and everything. Okay. Yeah. So that's quite beautiful. However, there's the other way, the second way going through this that is simpler. Um, People can say that, well, I'm cheating, I'm using too much of the regularity, and I'm using that L is uniformly convex and stuff like that. There's the other way, the cheaper way going through this, the second way, and I'm ending this today lecture by this. So there's a cheaper way of getting through this. Okay, you would have eta k converge to gamma uniformly on minus T0, right? And in fact, you would have that eta k dot is converging weakly to gamma dot, actually, right? Weakly. I'm being vague about which sense here. I mean, you can do Wittgenstein L infinity, uh, uh, or stuff like that, depending on topology. Or you can do weakly in L2. Sometimes that's enough. And then you can use actually the lower semi continuity property of the action functional, right? So you don't need, actually the limit is the same. If you go back here to the proof, what did you need to do? The left hand side is always h of xy. You don't need the equality here, right? What you only need is the inequality. So what you need is just the lower semi continuity property of the action functional. What you would need is that you only need lim inf k goes to infinity of the action greater than equals to minus t to 0 L gamma dot ds, right? That's the only thing that you need. And this is actually coming from the lower semi-continuity property, or semi-lower whatever, um, of the action functional, and that's it, right? I mean, that's the other way. That is a cheaper way, but I mean, for us, we have the whole regularity thing, and then that's everything is natural. Okay, so I'm done. Questions, concerns?
Yeah. So what happens with gamma as t goes off to negative infinity?
Um, so we don't know, right? I mean, so this proof only give us the existence of gamma, of a backward characteristics, or a calibrated curve, right? And then you see that we only using eta k to construct gamma in a locally uniformly way. So we are just, in a way, you see that we are using the uniform conversion, everything on each of the compact interval. And you see that by doing this, we only have the existence of gamma. And as earlier, when we had to understand more about the properties of gamma, like rotation vectors, like ergodic properties, and we needed to define the matter measures and stuff like that to understand those. But clearly that the question about understanding gamma deeply and in, I mean, more quantitatively, than we don't know. So just like, understanding is ergodicity, understanding it's sort of like how much of the space does it occupy, what's going to be the rotation vector and stuff like that. So that we know, but actually there's still something we don't know. I'll address that. But
Yeah. Thank you.
yeah, you're welcome. So you see, it's always that using what we have done so far is really mostly using really deep and nice intuitions, but many of the times that we are only using qualitative conversion, I mean, or compactness or stuff like that. So you see that I'm only using the seeing gamma on each of the compact interval. I see just its existence. I see nothing throughout this kind of truth, right? And same for matter measures. Um, the idea of matter measures, actually, I said about relaxation. I said about connections to um, to optimal transport. But actually, I forgot one point, that the idea of matter measures comes. You can say that it's earlier from Young's measures, right? Young's measures was some relaxation formulations that, when you cannot keep track with parts and stuff like that, then you could try to define Young measures. And again, one great thing was that Young measures was done by Young at Wisconsin. I mean, like in the 1950s, if I remember it correctly. But I did check with Paul Rabinovich and others that Young measures actually was defined in Wisconsin. So it's a great mechanism to bypass the lack of compactness to get to something weaker, and then that we can capture. But then, if you ask more, like, okay, so you can capture something weakly, what is that thing? Then sure, I mean, it's sometimes it's too weak that we haven't been able to understand it. So yeah, so it's always a trade-off. Any further questions?
So at the beginning, you mentioned this is not the maximal solution. Is
Yeah.
there any other kind of relation between the two? So the maximal solution is root KM solution and vice versa.
The so this is, again, there are a lot of weak solutions, right? I mean, this is just one way to design the solution, and this is different from the maximal subsolution. So the maybe let me just say it a little bit here. um, so there's some sort of so there's some related notion, is, I should have said, maybe instead, related notion, how should I define it? Normally I call it S. I remember that I call it S. Yeah, so there's a related notion called the maximal subsolutions with vertex X. Okay, so maybe let me call it S of X, Y. Okay, so vertex X going to Y. This is defined in the PD way. It's just gonna be the supremum of all WY minus WX. For W is a subsolution to the equation H of X. The W of X is less than or equal to C naught in the torus. And this is a very relevant, I mean, we have talked about subsolution and stuff like that, right? So this is the PD definition, and this is the definition in the dynamic term is infimum for all time greater than 0 of the action functional. in which I have gamma 0 starting at the vertex x and gamma t is the ending point is the y. Okay, so that's the maximal subsolution. And you know, this one so what is different is that I don't let t goes to infinity, right? The infimum is over all time, so that's why it's different. uh, and yeah, so the key point is that s of xy in general is different from h of xy. Okay, the maximal solution is different from um, the Pierce barrier. The maximal solution, because I don't kick the vertex to infinity, is gonna look pretty much like a cone, you know, because I'm starting at x and I'm defined this is xy is the cost of going from x to y. It's gonna be like that, and in general, as y maps to sxy is the maximal subsolution to the equation h of y ds of xy equals to less than equal to c naught in the torus. And at the vertex, I always, because this is for any time, so at the vertex I always have sxx is equal to 0. Okay, and y maps to s of xy is only a viscosity solution or a solution to the equation except at the vertex. Okay, so that's why I meant that they're different. So in general, it's only a subsolution at the vertex. However, there's a deep result. I don't know if I have time to come to that. Is that, however, there's a very deep characterization in PD is that this is a theorem. It might take me a few days to prove it. Is that x is in the Aubry set if and only if y maps to sxy is a viscosity solution or a quick-cam solution to the equation in the whole torus. Yeah, so that's the result. And again, I mean, this is a very uh, very big overview. It's might take me a few lectures to prove this. It's not too hard, but again, I need to develop the threshold and stuff like that. But you see that the difference, the key difference between maximal solution and the Pierce barrier is that for the maximal solution, I only take in for all time. So time can be 0, in fact. And that's why that at the vertex, the value is always 0. And I'm not kicking the vertex to infinity. Okay. Any other questions? Okay, so then that's good. Thank you all, and then I see you on Friday. Right, see you.